Chapter 20 Sticky Notes. So this chapter goes over what we call conventional energy alternatives. So they are better than fossil fuels, but still have some problems. The case study about Sweden, you don't need to know about that. So let's turn the page. Let's talk about on 554, the world's energy. So when we're talking about full-on energy, you need to know oil is number one in energy. So this includes electricity and transportation and heating. So oil is number one. Coal's number two, and then natural gas, and then biomass. So for electricity, coal is still number one in electricity, but it's declining pretty quickly because it's being replaced by natural gas. So you can see over here toward the end of the 2000s that coal is declining a lot, and you can see natural gas is rising. So you really need to focus on this because the graph ends almost at 2010, probably 2012 maybe it kind of looks like. So now we are about 8 years later, and coal has continued to go down and natural gas has continued to go up because we have fracking is a new technology that allows us to extract the natural gas. So we have more of it than we used to. And it's better actually. So this is a good thing because coal is really dirty compared to natural gas. So natural gas is the cleanest of the fossil fuels. But this is energy overall. So oil is still the most, and this is because of transportation primarily. And then down here you can see you have nuclear and you have hydropower and bioenergy, and we'll talk about what all of those things mean. All right, so first we're going to start with nuclear power on 556. So you need to know how nuclear fission works. So you need to understand this diagram right here. And you need to know that what we use in nuclear power is uranium-235. So this is the isotope of uranium. So you need to know it's uranium-235. It's in a positive feedback loop and a chain reaction. So down here I sketched it a little bit for you. To start the chain reaction, you have a neutron that hits a uranium atom. And that uranium atom splits, and you get all this energy from the split. Boom, energy. And then it releases more neutrons, which hit more atoms, which boom, energy, and then neutrons. So it's the neutrons that keep hitting the uranium atoms. So a chain reaction is all a bunch of neutrons. So on a test question, that's what you want to look for is neutrons, which do neutrons to neutrons. So it's positive feedback loop because it just keeps going and going and going. Once you start a nuclear chain reaction, you really can't stop it. Okay, so half-life is the time it takes for half the atoms to give off its radiation and decay. U-235, the half-life is 700 million years. So that's kind of the problem with uranium is that it's going to last a long time. Up here, you need to know really on page 557 how we get power from nuclear. So it's very similar to coal, except here we have our nuclear fuel rods in here, and it's in a containment building. So this is like super thick concrete. And then we still have the water. So the chain reaction's occurring in here in the reactor core, and the heat is going to steam water, and that steam spins a turbine, which releases electrons in a generator. And then we cool down the water in these cooling towers. So here, instead of burning coal or natural gas or oil, we have a chain reaction of uranium with neutrons hitting it to release the energy. So you need to know also on page 557 still that how we get U-235 is that we mine U-238. So the isotope of uranium that comes out of the ground is uranium-238. and we enrich it to U-235. So it's called nuclear enrichment. And then this U-235 is formed into smaller pellets, and the pellets are made into fuel rods. And so that's what happens for nuclear power. So this is a picture of the enriched uranium, and we encase them in metal because they're radioactive and they're dangerous. And then we also put them in water to cool them down. But the water has to constantly be refreshed because it gets too hot, and then it can't cool down the reactor, and then the reactor explodes, which is what happened in Fukushima, Japan. We'll talk about that in a minute. All right, turn the page to page 558. So one of the benefits, so we are now building some new nuclear power plants because it has no air pollution, no greenhouse gas emissions. It has thermal pollution, so the cooling of the reactors takes place with water, and then the water can be discharged and cause thermal pollution in a body of water. But no greenhouse gas, no air pollution, and so this is why we're building more, because we need to reduce our greenhouse gas emissions. We use it for electricity, not heating, not transportation, so we only use nuclear power for electricity. This is called nuclear fusion, which is the sun's energy, which we don't actually know how to do in the lab. If we knew how to do this process, which is combining atoms to get that energy, that would be all the power we'd ever need. It would be so powerful, but we don't know how to do this yet. Now, there's people working on it, but right now we can't do nuclear fusion yet. Okay, up here you can see this is a nuclear power plant, and you can see the body of water here. So this can, if they don't let water cool enough in their cooling ponds and it gets into this lake, river, I'm not sure what this is, it can cause thermal pollution, which can lower the dissolved oxygen, and then the species that live there, if they're not adapted to warm water, they're going to have to leave. This is also a picture of the only nuclear accident that we've had in the United States, called 3 Mile Island. It was considered a near miss, but it says no health impacts, but there is some controversy over that. The official government stance is there's been no negative health effects, but private universities that have been tracking it say, yeah, there's been high rates of cancer in the areas surrounding this. So that's Pennsylvania. The next accident you have to know is Chernobyl, and this happened in the old Soviet Union, which is now, the Soviet Union broke up in about 1990, and it formed mostly Russia, but also some other countries. So one of the other countries that was the Ukraine. So Chernobyl is now in the Ukraine, and it exploded due to basically human error, ignoring signals, ignoring problems, and it was really, really, really bad. All right, going on. Lots of people died from this too as well. Okay, so you need to know what happened at 3 Mile Island in the US. It was a nuclear meltdown. In Chernobyl, which is in the current Ukraine, it was an explosion and radiation spread all over Europe. In Fukushima, Japan, it was an earthquake which caused a tsunami, which flooded the nuclear power plant and shut off their power, so they couldn't pump the water in and out to cool the nuclear reactors. So they ended up with explosions and massive radiation exposure. Radiation exposure in particular causes thyroid cancer. On the AP test, don't just write cancer, it's specifically thyroid cancer from radiation. This is Chernobyl, and you can, depending on the winds, the radiation from Chernobyl spread all over Europe, and again, it depended on the winds, who got more. So the places where the winds spread it in higher concentrations, you'll have here in your darker colors. Over here on page 561, what happened in Fukushima, and you can see the tsunami coming towards the nuclear reactors here at Fukushima. is that off the coast of Japan, they have a convergent plate boundary with subduction. And so the displacement of the water, so one plate slid below the other, and this would be the island of Japan right here. And then the plate snapped back up, and then the water, boom, went like this and created this big tsunami wave. So it's the displacement of the water that caused the tsunami. The next page talks about the health impacts of Chernobyl. In particular, you need to know it's thyroid cancer, which is here in the neck. So this boy had thyroid cancer afterwards. A lot of people died of acute radiation poisoning too right away, but then in the next several years, people came down with thyroid cancer. Okay, page 564. So one of the big problems we have with nuclear energy is, what do we do when the fuel rods are done? We can't get our power out of them anymore, but they're still radioactive, and they're going to be radioactive for tens of thousands of years. So currently we have wet storage underwater, we have dry storage here in casks. They currently are stored at the facility. So here we go. Most high-level waste is currently stored at the reactor sites. So that tells about it here. Uranium is non-renewable and it's a metal, so you need to know those two facts about uranium. We have long-term storage plans, kind of, in a place called Yucca Mountain in Nevada. So Congress voted to build this site, and they were in the process of building it, and then it was sort of like not being built anymore because of opposition from Nevada, who said, we don't want to take the whole country's nuclear waste in Nevada. So it is still designated the place, but nothing's being done. So a common problem on the AP test is this. The question is, where is spent nuclear fuel being stored? And kids want to choose Yucca Mountain because they remember Yucca Mountain. But it's not. That's the long-term plan, but it's not currently there. And in my opinion, it probably never will be there. So you need to know it's currently stored at the reactor sites. And I underline this because that's really important. You have to know it's currently being stored at the reactor sites. All right, turning the page. Now let's go on to biomass. So over here, biomass is basically all these kinds of things. So sources of biomass is a living thing that we burn. Wood, charcoal. Charcoal is made from burnt wood. Manure from animals, we can burn that. Corn, sugarcane, soybeans for biodiesel, algae for biodiesel. For generating electricity, crop residues, we can burn these things instead of coal or natural gas. We can burn trash from landfills too. Okay, so burning biomass emits less, but it still emits carbon dioxide, particulate matter, carbon monoxide, NOx, and VOx. So you need to know these are the air pollutants from burning biomass. Now, it's less than fossil fuels. So biomass is much less air pollution, much less greenhouse gases than fossil fuels, but it still does it. It can cause deforestation in places where they're relying on wood for heating and cooking. This used to be a forest, but poor people need it. You can't blame these people. They're trying to survive. And so that's a problem, though, deforestation. If you're growing biomass like for sugarcane or corn for ethanol, it can deplete the soil of nutrients. And if you don't fertilize it or take care of your soil, that can happen. So wood is a primary energy source in developing countries because it's cheap and readily available in firewood or charcoal, which is burnt wood. So, but the problem is it gives these people asthma from indoor air pollution if they're burning it indoors, not if they're not. If you're burning wood indoors, even in the U.S., some people do this for heating or cooking, you can install ventilation systems that help with this problem from the air pollution and asthma from burning wood or other forms of biomass.